Here we'll design another type of combinational logic circuit, that is BCD to Excess-3 converter. We know the function of BCD to Excess-3 converter. In one side, if we provide BCD input, in another side we'll get Excess-3 output. When we say the input is BCD, that means this number will start from 0000 up to 1001. That means the maximum value of input can have 9. So using 4 bits we can have 16 combinations. So 6 of the combinations can be taken as don't care condition, because those inputs will never come as the input is BCD. So we need to design this box BCD to Excess-3 converter. First of all, let us construct the truth table for this. In input side, we have A0, A1, A2, A3. And in the output side, we have B0, B1, B2, B3. So in input, we can have 16 combinations, 0000, 0001, 1000, 1001. If we write the corresponding decimal numbers, this is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. As I told you earlier, as the input is BCD, so we'll get the values starting from 0000 up to 1001. So remaining inputs from 1010 up to 1111, we can consider them as don't care. Now let's construct the output for each input case. When we have A0, A1, A2, A3, which is equals to 0000, the Excess-3 code of 0000 is 0011. We need to add 3 with this corresponding BCD numbers. So Excess-3 code of 0001 is 0100, 0101, 0110, 0111, 1000, next 1001. So up to this much will be our domain. Here we can see there are 4 output variables. For each output variable, we need to figure out the simplified function. If we use kernel map, so we need to use 4 kernel maps. Let us place 4 kernel maps for B0, B1, B2, B3. This is the first kernel map. Second kernel map. Third one. And the fourth one. We will simplify the function B0 using this kernel map, B1 using this kernel map, B2 using this kernel map, and finally B3. Now let us find where are we getting B0 equals to 1. B0 equals to 1 at 0 position here, 1, 2, 3, 0, 1, 2 at 2 position, 3, 4th position, 4, 5, 6, 7, then 8th position, 9, 10 position, 11 positions are considered as don't care, so we are placing don't care here. So this is the mapping for B0. Next, let us map the B1s. We have 1s at 0th position, 0, 1, 2, 3. We have next one at 3, then 4, 5, 6, then 7, 7 is here, and 8 here, and these are the don't care conditions. Next B2, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and remaining positions are don't care conditions. Finally B3 equals to 1 at 5, 6, 7, 8, 9. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and these are the don't care conditions. Now let's combine the adjacent cells containing ones. We have this as adjacent cells containing ones. So we can write B0 equals to A0 prime. Now let us go for B1. We can take this box and we can take another box here, and B1 can be written as A1 prime A0 prime plus A1 A0. For B2 we can take these 4, another 4 can be taken here. For this one we can take 2 boxes. So B2 can be written as A2 A0 plus A2 prime A1 plus A2 A1 prime A0 prime. Finally B3, we can take these adjacent cells. We can take these 4 and we can take this 4. B3 can be written as A3 plus A2 A0 plus A2 A1. So we have got simplified version of B0, B1, B2, B3 using Kernel Map. Now let's draw the logic diagram. There are 4 inputs: A0, A1, A2, A3. The output B0 is A0 prime. This is B0 output. The output B1 is A1 prime, A0 prime. We have A0 prime here, A1 prime. They will be ANDed. A0, A1. They will be ANDed. And the outputs will pass through OR gate. Will get B1. The B2 function, we need to make A2 A0. We have A2 A0 can be taken from here. They will be multiplied. A2 prime A0, they will be ANDed. Finally A2 A1 prime A0 prime. A2 A1 prime A0 prime can be taken from here. They will pass through another AND gate. All these outputs will pass through OR gate. This is B2. Finally B3, A3, next A2 A0, which can be taken from here, A2 A0, A2 A1, we have A2 here, and A1 can be taken from here. This is the B3 output. Now we have this circuit. Inside this box we have this logic diagram, and these are the inputs and these are the Excess-3 outputs. Next we will design another combinational logic circuit, that is BCD to 7-segment decoder. Before we start designing this, we need to know what is 7-segment decoder. Whenever we have a BCD output in binary form, that means 0 is represented by 0 0 0 0, 1 is represented by 0 0 0 1, 2 is represented by 0 0 1 0. In this way we can represent up to 9, which is represented by 1 0 0 1. Now as an engineer we understand this 0 0 0 1 is the representation of 1 in BCD format, but in order to express this number to the mass people, we need to express the number in a way so that people can understand. That's why we use 7-segment decoder. In 7-segment decoder, we have this type of formation. There are 7 segments. These are the segments, and each of the segments is connected with LEDs, light emitting diode. So this is one LED, this is another 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 LED, and this is another LED. And there is another LED which represents the dot sign. Each LED is connected with one unique connection. Suppose this is connected with this LED, this is connected with this LED. So we have 1, 2, 3, 4, 5, 6, 7. We are considering the 7 segments. So if we name the segments, this is A, B, C, D, E, F, G. So this lead is connected with A LED. In the similar fashion, this is connected with B LED, C, D, E, F, G. Now, in BCD to 7-segment decoder, we'll be designing a decoder which will take 4 inputs, this A0, A1, A2, A3. These are the BCD inputs. It will take BCD inputs, and there will be 7 outputs which will produce the corresponding decimal number in a way so that the number is easily understandable to the people. For example, using the 7-segment display, we can represent 0. How? If we switch on A, B, C, D, E, F, then it will look like this. B, C, D, E, F. It will look like 0. If you want to show 1, whenever we have 0, 0, 0, 1 input, we want to show 1. So we need to switch on only B and C light. So this will look like this. In order to show 2, you need to switch on A, B, G, E, D. So A, B, G, E, D. It shows 2. Similarly, 3 can be represented in this fashion. If you switch on A, B, C, D, G. 4 can be represented by these lights. 5 can be represented by these lights. 6 can be represented by switching on these lights. 7 can be represented by switching on these lights. 8 can be represented by switching on all the lights. And finally, 9 can be represented by switching on all the lights except E. Now, in BCD to 7-segment decoder, we'll be designing a circuit in a way where there will be 4 inputs. These inputs are in BCD. It will take these inputs, and there will be 7 outputs: A, B, C, D, E, F, G. This is BCD to 7-segment decoder. Inputs are A0, A1, A2, A3. Outputs are A, B, C, D, E, F, G. Inputs are in BCD format. Whenever we say input is in BCD, that means this number can have range from 0000 to 1001. Now, in order to design BCD to 7-segment decoder, let us draw the truth table first. In the input side, we have A0, A1, A2, A3. In the output side, we have A, B, C, D, E, F, G. In the input side, we have 0000, 0001, 0010. If we write the corresponding decimal numbers, 0000 represents decimal 0. 1, 2, 3, 4, 5, 6, 7, 8, 9. The number starting from 1010 up to 1 1 1 1, we can take those as don't care. So these are the don't care conditions. Now whenever we have input 0 0 0 0 0 0 0 0, we want to show 0 here, so we need to switch on A, B, C, D, E, F. So we need to switch on these lights A, B, C, D, E, F except G. So all the variables will have one output except G. Then to represent 1, B and C will be ones and others will be zeros. To represent 2, A, B, G, E, D. A, B, G, E, D, these are to be 1, others will be zeros. To represent 3, F and E should be 0. This E and F should be 0, others will be 1. To represent 4, F, G, B, C will be 1. F, G, B, C will be 1. Others variable will have 0 value. To represent 5, B and E should be off. B and E should be off, others will be 1. To represent 6, A and B should be off. A, B should be off, others will be 1. To represent 7, A, B, C should be on. A, B, C should be on, others will be 0. To represent 8, all the lights should be on. To represent 9, all the lights should be on, A, B, C, except E and D. So D, E should be off. And these are the don't care conditions. Now there are 7 output variables. So we'll have 7 functions which are needed to be simplified. Let us use Kernel Map for the simplification process. Here we have placed 4 kernel map. This kernel map will be used for simplification of A. For A, this is for B, this is for C, and finally this is for D. Remaining kernel maps will be designed once we complete these 4. Now for A function, if we map the ones, we can see we have ones at 0 position, 2 position, 3 position, then 5th position, 7, 8, 9. So let's place the 1, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And these are the don't care conditions. We can put don't care conditions. Similarly for B, we have 0, 1, 2, 3, 4. 0, 1, 2, 3, 4. Then 5, 0, 6, 0, 7, 8, 9. These are the don't care conditions. Now for C, the ones will be placed at 0, 1, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And these will be the don't care conditions. Next for D, we have 0, 1, 1 will be 0, 2, 3, 4, 5, 6, 7, 8, 9. And these are the don't care conditions. Over here at 9 we have 0, so this one will not be here. Also for A, we have 0 at 6th position, so this one. Let us start the simplification process. You can take this box, you can take this box, you can take this box, finally we can take the corner boxes. Now the simplified version of A can be written as, the name of this red box is A3 plus Name of the green box is A2 A0 plus A0 A1 plus the corner boxes A2 prime A0 prime. Next, let's simplify function B. We can take this box. For this, we can take 8 adjacent cells. For this one, we can take 4. And for this remaining one, we can take this 4. So function B can be written as B equals to, the name of this red box is A3 plus A2 prime plus A1 prime A0 prime plus A1. Next, let us simplify function C. We can take 8 boxes here. Next, we can take this. Finally, for this one, we can take this box. So the function C can be written as A3 plus A1 prime plus A2 plus A0. Next, let us simplify D. 4 adjacent cells from here. 4 adjacent cells at the corners. For this one, we can take 4. And for this one, we can take 2. Now D equals to A1 A0 prime plus A2 prime A1 plus A2 prime A0 prime plus A2 A1 prime A0. Next, we will draw the kernel map for remaining 3 variables E, F, G. 0, 1, 2, 4, 5, 6, 7, 8. And here there will be don't care conditions. Again, for F, we have ones at 0, 4, 5, 6, 8, 9. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And these are the don't care conditions. Finally, for G, we have ones at 2, 3, 4, 5, 6, 8, 9. So 0, 1, 2, 3, 4, 5, 6, 8, 9. And these are the don't care conditions. Let us simplify E first. We can take these 4 and we can take 4 corners. So the simplified function of E can be written as A1 A0 prime plus A2 prime A0 prime. Next, for F, we can take these 8 adjacent cells. We can take 4 from here. We can take another 4 from here. And finally, we can take 4 from here. Now, the simplified version of F can be written as A3 plus A1 prime A0 prime plus A2 A0 prime plus A2 A1 prime. Finally, let us simplify G. We can take 8 adjacent cells. For this, we can take 4. For this, we can take these 4 adjacent cells. Finally, we can take these 4 adjacent cells. Now, the simplified function of G can be written as A3 plus A1 A0 prime plus A2 A1 prime plus A2 prime A1. Now, let us construct the logic circuit. Here we have 4 inputs, A0, A1, A2, A3. This is A3. This line represents A3 prime. This is A2. This line represents A2 prime. This is A1. This line represents A1 prime. This is A0. This line represents A0 prime. Now first, let us draw the logic circuit diagram for A function. A is equals to A3. This is connected, plus A2 into A0. A2 into A0. These are connected and they will pass through AND gate. Then A1 into A0. They will pass through AND gate. Finally, A2 prime into A0. They will pass through AND gate. These are connected. All these outputs will pass through OR gate. This is the output function for A. Let us draw the remaining logic circuit in the next page. Now for function B, we have A3 plus A2 prime. A3 can be taken from here. A2 prime can be taken from here. These two are connected. Next, A1 prime, A0 prime, A1 prime, A0 prime. They will be ANDed. They are connected here. Finally, A1 into A0. A1 into A0 can be taken from here. All these outputs will pass through OR gate. This is an OR gate and we'll get B here. Next, let us draw the diagram for C. A3, A2, A0 prime, A0. We have A3, A2, A1 prime that can be taken from here, and finally A0. They are connected here, and this will pass through OR gate. We'll get C. Next for D, A1, A0 prime. A1, A0 prime. They will pass through AND gate. They are connected here. Next, A2 prime, A1, A2 prime, A1. They will pass through AND gate. Here they are connected. Next, A2 prime, A0 prime. They will pass through another AND gate. We have A2 prime from here and A0 prime from here. They will be connected. All these will pass through another OR gate. We'll get D output. Next for E, we need A1, A0 prime, A2 prime, A0 prime. Each product term is readily available here. This is A1, A0 prime, and this is A2 prime, A0 prime. They are connected and they will pass through an OR gate. We'll get E. Next, we need to have A3 plus A1 prime, A0 prime. We can take it from here, but I am redrawing it here in order to make a cleaner picture. So A1 prime, A0 prime. They will pass through AND gate. They are connected. Next, A2, A0 prime, A2, A0 prime. They will pass through another AND gate. They are connected. Finally, A2, A1 prime. They will pass through another AND gate. All the outputs will pass through OR gate and we'll get the function F. These are connected. Finally, we need to draw the logic circuit for the function G. One will be taken from A3. Another one will be taken from A1, A0 prime. We have A1, A0 prime. We can take it from here. A2, A1 prime. A2, A1 prime can be taken from here. Finally, A2 prime, A1. A2 prime, A1. They will pass through AND gate. They are connected here. This is connected here. This is connected here. This is connected here. All these outputs will pass through OR gate and we'll get G function. So we have got A, B, C, D, E, F, G. This is the logic circuit diagram of BCD to 7-segment decoder.